So now, almost every gamma ray tool in the world now is calibrated in API units. Doesn't matter whether you're in Lithuania, Singapore, or you're in Kansas. API simply stands for American Petroleum Institute. They have offices in Washington, D.C. where they shuffle paper. But down in Houston, and specifically the University of Houston, there's a test pit down there. In fact, you can even rent it. I think it's about $150 a day. And in there, they have standards then for, among other things, the gamma ray tool. Way back when, what they did was they took some cement, they put some radioactive isotopes in it, probably added Tabasco sauce and a few other things, shook it up, stirred well, and said, let you be 200 API units, with the idea that a typical mid-continent shale, whatever that is, would read kind of around about 100. So the notion is then it's an arbitrary scale, but at least it's consistent. It gives us some kind of scale of reference to do comparisons. And very commonly you'll see it scaled between 0 and 150, but sometimes a logging engineer will choose a different scale, most particularly if you have some really hot sections. But in all cases, when you're looking at logs, the logging engineers are trying to help you out. On the one hand, they're not trying to herky-jerk the scales all over the place, but have something that you're used to seeing. And just as Richard was picking up, just looking at the logs themselves, reading the raw logs, and in my notion it's kind of like reading sheet music. You get used to it, they try and set up in a way that you can understand. As Richard was demonstrating by the digits, then you can rescale them to really have that music sing out for you so you can read the logs directly before you start to actually crunch the numbers and get them out. So looking at the section here then, we see that 0 to 150 with a backup scale of 150 to 300 so that when it goes off scale it reappears on that backup scale there. Then in terms of what we see, the fundamentally limestones down here read fairly low gamma ray typically, if nothing happened to them following deposition. So originally these were calcite muds being deposited out in some tropical sea, and they had a very low gamma ray. Then they get lithified, and if nothing happens, you'd expect them to read fairly low gamma ray. However, in diagenesis, every rock has a history. You can have uranium-bearing solutions, which is what you very often see in the chase group, and we'll see an example there. Now going up above, here's our unconformity going into the Pennsylvanian Cherokee group. Well, here we have a Cherokee sand right here, reading a little higher than 0 for sure. And that's because the sandstones then, yes, they're composed of quartz grains, but they have a lot of other stuff in there as well. Clay minerals, micas, potassium feldspars. If you have something that's arcosic, then yeah, that potassium is going to zing in then as high radioactivity. Then above, as we move into it, we move into shales and shaly sandstones. And as we look at this curve here, it's kind of a moving average in that sense. That the gamma ray tool is being brought up through the hole, they're counting radioactive particles, and they're counting within a certain time window. So on the one hand, they try to smooth it out a little bit so you don't have the noise, the kind of chattering that you'd hear on a Geiger counter or the flicking of the needle. But they don't over smooth it because they don't want to smooth out the thin beds. But we have to bear that in mind. This could be a fairly clean sandstone that's fairly thin and being averaged out, or indeed that could be a shaly sand. How we look at this, we go up into the shales. Fundamentally then we have what is a shale log, unless we got some uranium in there. And that's one of its main features then to be in track 1 to allow us to pick tops and bottoms of potential reservoir formations, the non-shales, at the same time get an idea of the degree of shaliness. So what's going on in the shales? They're supposed to read around about 100, maybe a little higher. Well, you've got potassium, and that'll be in the illite. The clay mineral illite has potassium in its crystal lattice. And also in a gray shale, one that doesn't have that much uranium, you have a fair amount of thorium. Nobody's really actually explored why that thorium is there, but it is. Some people say the thorium is on the surface of the clay minerals. And they say that because thorium is an awful big atom to try and cram into a lattice. Other people say if you get a microprobe, you can actually see small particles then of radioactive minerals which have high thorium. part of the reason we don't know so much about shales on logs is because we ignored them all these years. We said, who cares? They're seals. It's only recently we started to play catch up to say, hey, what's going on in these shales, so we can start to think about gas shales and so on. So even as we speak, people are trying to do a lot of research then to find out what's going on. Now, what about this business about a typical mid-continent shale reading about 100? Well, let's look at this section. We are in Waubonsee County, Kansas. It's a long section going from 600 down to below 1500. We've got a big scale here, 0 to 400. So I've expanded it because we've got these events here which are highly radioactive. So fundamentally, you're seeing over here, those are the limestones, the Lansing, Kansas City, maybe about 20 API units, something of that sort. Then we've got these guys out here. Those are what in outcrop would be gray, simply gray shales. And I look at those and I think, I would pick more of 120 being typical based on this thing here. Now otherwise though, we've got these are the black shales. So if you see them in outcrop, yes, they're black. They've got a lot of organic matter in them. Often in the Lansing, Kansas City, a lot of phosphatic material as well, phosphate nodules, and this spiking is because of the uranium content. If we took out the uranium content of these black shales, it would simply slump back to about 120. So in terms of potassium thorium, there's not much difference between a gray shale and a black shale. The reason I can say all these things about that is because we'll be looking at spectral gamma ray logs where we break it out and we say, let's check it out and see what the differences are. So here we have the notion of a conventional gamma ray log, an ordinary gamma ray log. It's simply counting the number of gamma rays that come into the housing of the tool. But we can run a spectral gamma ray log, and what it does is it focuses on the fact that each radioactive isotope emits a gamma ray of a specific energy. So rather than counting all of them regardless, they set up windows then within this range here and count how many particles within the windows. So looking up here, we see potassium 40, we have a spike. It's a single isotope. We look at the thorium, and here's a spike here they often focus on, that's thallium 208. It's not thorium, it's a granddaughter. It's radioactive. Originally, its grandmother was thorium. We look at uranium, and here's another distinctive spike, bismuth 214, which again is a granddaughter product of the uranium series. So in a spectral gamma ray log, what they'll do is they measure gamma rays within windows on that range and put them back together to figure out how much potassium, thorium, and uranium there are. And this is the typical presentation. Over in track 1, you'd see gamma ray API units, and you see something that's usually labeled SGR. Some people say the S stands for standard, other people say spectral, but this would be what you would measure on just a conventional gamma ray log. Then we have the CGR, and that's the computed gamma ray log, and that is simply the sum of the thorium and potassium. So the way we look at it then, if you're interested in shale, this CGR is much more a response to the shale content because it's picking up the thorium and potassium associated with that shale. Between them, there's big separation. That's the amount of uranium. So if we were looking at an ordinary gamma ray log, we'd say it looks shaly all the way through. This part says, no, I don't think so. That's cleaning up, and it simply has a fair amount of uranium. Now, by setting up those windows then, we can actually partition out the amounts. This will be printed in on a hard copy. We have thorium, parts per million, uranium in parts per million, and potassium in percent. So they'll actually be put at 3 separate curves. Now when you see spectral gamma ray log, you think expensive. I mean, that very word spectral says, whoa, but it's really not that much more than a conventional gamma ray log. Many logging service companies, they just run the spectral anyway, and then you simply decide whether to pay for it.